All right, we are at section 34.3 and analysis model wave under reflection. Let's share the PowerPoint, and you can see on the left-hand side, the um, A and C, you have uh, what is called specular reflection. The smooth surface, the light's coming down. We talked about the parallel uh, rays of the light coming and they hit, and they all bounce up uh, again in parallel. So you have a smooth surface, a mirror surface. It reflects. It reflects. You can there's my face. It reflects. Whereas the rough side, it doesn't reflect. I can point it to the light, and it's diffused. You can sort of see the reflection, but it's diffuse reflection. This is specular reflection. A smooth glass surface reflects everything. Um, so the incident ray, that's the ray coming off the source light, uh, hits at an angle of theta 1. The reflected ray and the normal all lie in the same plane, and theta 1 prime equals theta. So the normal, just like we've always defined normal, it's normal to the surface. The normal, here I'm using a point, but it's more of a line. The normal to the surface. You have the incident ray coming in at theta 1, and the reflected ray at is theta 1 prime. So you have the incident ray and you have the reflected ray. Um, so let's do a little quick quiz. In the movies, you sometimes see an actor looking in a mirror, and you can see his face in the mirror. It can be said with certainty that during the filming of such a scene, the actor sees in the mirror his own face, your face, the director's face, the movie camera, or it's impossible to determine. Well, he's looking at the movie camera. It's just a trick to make it look like he's looking at himself in the mirror, but it's actually he's looking at the camera, and the camera's looking at his reflected face. Okay, retroreflection. Retroreflection, we see examples of this all the time. They put the retroreflector is when you have you put a mirror, and then 90 degrees to it, you put a mirror like this. So any light coming here will hit the bottom mirror and be reflected back. I don't know that you could necessarily see that. And if you do 3 of them, you form this corner. It's like a 3-dimensional reflector. So any incident ray coming in will go back out. So this panel, in 1969, a panel of many small retroreflectors, many small reflectors, were replaced on the moon by Apollo 11 astronauts. So a laser beam from Earth was reflected directly back on itself, and the transmit time was measured, and it was used to determine the distance to the moon with a certain uncertainty of 15 centimeters. 15 centimeters, it's about 15 centimeters. So B is an automobile taillight has small retroreflectors to ensure the headlight beams are reflected back toward the car that sent them. A light ray hitting a transparent sphere at the proper position is retroreflected, and that's what they use. They use these little microspheres to reflect, and they kind of put them on surface and then make retroreflectors, such as the stop sign here. Stop sign, they put them on tennis shoes, little reflector vests. They're embedded with these little microspheres that reflect light backwards. So the stop sign appears to glow in the headlight beams because the surface is covered with a layer of many tiny retroreflecting spheres. And then they use little mirrors in films. You can in movies you can see this is the leg of an ant to give scale to these little mirrors that are used. The mirror on the left is on, and the one on the right is off. So depending on how it angles, and it can even do particular angles so that you can vary the intensity. You can vary the intensity, the brightness of the pixel is determined by the total time interval during which the mirror is on in the on position and during display of one image. There's usually sets of three, one for each primary color, red, blue, and green. Movies can be displayed with up to 35 trillion colors. Okay. And so since the movie is digital, the movie doesn't degrade as it would if it were a piece of film. Okay, let's go to the analysis model. So this concept of a wave under reflection is not only for optical purposes, but it's also like for sound waves from an orchestra that reflected from a band shell out to the audience. You can see different shapes that they use for the band shell. A mirror is used to deflect a laser beam in a laser light show. That's how the laser itself can't move, but they draw these images. Like you go to Fiesta, Texas, you see the laser light. It's actually mirrors. The laser light is pointing in the mirror, and it's the mirror that can move very quickly to make these images. Your bathroom mirror reflects light from your face back to you to form an image of your face. X-rays deflected or reflected from a crystalline material create an optical pattern that can be used to understand the structure of solids. And we'll stop there. And the next, oh, I must have missed a theta prime equals theta 1 prime equals theta 1. We already discussed that. And we'll stop here and we'll go to refraction later in the next video.